Hey guys, welcome to my channel. In this video, we're gonna discuss how to implement a minimum spanning tree using Java. So we're gonna look at this USACO problem here. So let me note a couple of nuances. So in general, in a minimum spanning tree, you choose the edge cost that has the lowest value, right? Without any considerations. But here we have to make sure that the edge cost is at least as big as this value c, which is given to us as inputs. And here we don't actually we have edges between every vertex and every other vertex in this particular question, so it's no big deal, and we use this as the parameter to calculate the edge cost between two vertices. So those are the two nuances. So let's get right to the solution. So we take input first, right? So the thing to note here is we're going to use a data structure pair which keeps track of the x coordinate and the y coordinate. So it's not a big deal, just letting you know so the code makes more sense. And here's where the actual algorithm starts. So the min val is an array. So basically we have n nodes, right? And so the min val basically keeps track of. It's useful for the vertices that are not part of the minimum spanning tree yet. So for those vertices, we need to choose the one which has the lowest edge cost, right? So we're going to use minval as like the thing to store all those edge costs, the minimum edge costs, and we're going to pick one of those. So first we just fill the minval with 1e9 because we really don't have any values for it yet. So as always in any minimum spanning tree, you can start with any vertex because vertex by itself doesn't have any edge cost. So, but it's easier to just start with the zeroth vertex. So I'm gonna just add the zeroth vertex. We don't actually have to show it. So basically we calc from the zeroth vertex to the ith vertex. So basically every other vertex that's not part of the minimum spanning tree. So what the recalc here does is it calls this function, and the if condition basically checks the Euclidean distance between the zeroth vertex and the current vertex we are on is basically greater than or equal to c, and if it is, it basically updates that using this mat.min. Um, that's what it does basically, and that's what the minval is supposed to do. Hope that makes more sense now. And the cost is what we are actually going to output, right? And basically we recalc this, and we have a priority queue, so we're using Prim's MST with a binary heap. So we have a priority queue, and we have a comp function, comp class. So here's the comp class. You can look it up on Geeks for Geeks how I did it. It's very easy. It really takes a lot of coding for that. Just that basically says how to compare two keys. I mean, if you don't say it, it will just sort them, and that's not really useful, right? Because you have other data structures like tree set. If you really want to sort, we want to sort it according to a particular key. So the priority queue does its thing. We just add all the vertices. That's basically every vertex but the zeroth one, which is because the zeroth one is part of the minimum spanning tree. So we have a while loop. So while the size is greater than 0, so max what p.poll does is just pops the minimum value in the priority queue and updates itself. So this condition just makes sure. So let's think about a scenario where you have a vertex, but all of the edges from the vertex are less than the c, the threshold we have to cross. What does that mean? That means we can't do a minimum spanning tree because we can never access that particular vertex. So this basically checks if the min val is ever updated for that particular vertex, and if it's not, just break, and we're gonna out dot -1. But if it's not, we're just going to update the cost by the min val of that particular vertex we just added to our minimum spanning tree. So this part deals with updating the actual priority queue itself. So priority queue, the subtle thing about them is even if you update the comparator, so the comparator basically compares the min val of the two integers, right? So even if the min val is updated, the comparator doesn't update itself. So it's going to use the old comparator values. So even let's say you added a vertex to the minimum spanning tree, and for some of the other vertices that are not in the minimum spanning tree, you have new min vals, but in the comp it doesn't update itself. So to take care of that, we're gonna basically have a new. We're just gonna redo the adding part, the part we did here, p dot add. We're basically gonna do it, but we're just gonna have a array list, temporary array list that contains all the elements. And this time, because we created a whole new priority queue, this time it will make sure it uses the most latest values of min-val. These. So we do that after every iteration. It doesn't really cost a lot of space, memory. It probably costs some memory, but it's still doable in the time. So that, and if we had any problems, we'll just out.println -1, which means there is no minimum spanning tree. However, if there is one, we're just going to print its cost. So that's the algorithm. And the running time is pretty good because it's prim MST. So generally it would be m log n, or it could be n log n, because m and n are not much different. But it's just going to be m log n, which is pretty fast for this problem, because yeah, it's going to run pretty fast, because the n is like at most 2000. Yeah, so that and log n would be some more like, and the constants are not really a lot, and it's much less than 1 billion operations, which is how many a computer can do in a second. So that's not really a big deal. So that's the MST. Let me know if you have any questions, or yeah, I'll see you in the next video.